All right, welcome to Quarantined Math, day one for Algebra 2, featuring our special guest star, Michiru, the Siamese cat. And if you're in multiple on my classes, you'll know by this point she does not stay still very well, and she's probably going to leap at the camera here soon. And there she goes. So what we're going to be working on today is the beginning of that packet that we passed out, those rational equations, like we started talking about last week. You know, we're going to be taking all of the factoring work that we were reviewing before we got out of school and putting that into effect by trying out some of these rational equations with simplifying both the numerator and the denominator, and then trying to effectively eliminate any amount of redundancies in the equation itself. All right, here's what we are going to be working on today in Algebra 2. On the first page of your packet, we are looking at questions 6 and 7. We've done, I believe, at least 1 through 4, maybe 5 in class, and 6 and 7 are some pretty good examples for us. So these are rational expressions that we've mentioned before, equations that are effectively more complex than they need to be. And what I mean by that is whenever we look at these equations, we see lots of cubed variables and big numbers and long polynomials. And in reality, a lot of these can actually be written much simpler than they are now, meaning that we can rewrite these, take out all the nonsense and redundancy, and just strip it down to the bare bones equation of what it has to have there. So that's what we're going to do here. Now, the way to do this is through taking a look at all the numerators and denominators and applying, factoring methods to them. The first step we always want to look at when trying to simplify a numerator or denominator is asking ourselves, can we factor it out? And if we can't, then we want to go to the box method or difference of squares. The big thing you want to really look at these is factoring it out means seeing, is there anything that all the terms have in common? Are they all divisible by a certain number or a certain variable that we can take out? After we do that, or after we determine if we can do that, then we want to look at box method and difference of squares, which we do the box method if we have a polynomial, an x squared, x, and constant equation or expression. And difference of squares is when we have only two terms, but everything there are perfect squares and they're subtracting. So we're going to see all of these today. We're going to work our way through them and talk about how to do them just to remind us. We got through the factoring worksheet the other day, so hopefully we're on good ground with that, but we'll be explaining everything. So we're going to start with number 6. When we take a look at number 6, what we want to do, like I said before, is take a look at the numerator and the denominator and simplify it, break it down, factor it, however we can. So we always start with factor it out. Is there anything that both parts of our numerator have in common? Well, luckily for us, there is. Both of these whole numbers are divisible by 3, and both terms also have, at minimum, 1a. Whenever we're talking about variables, we always want to look at how many each term has at minimum, meaning that if we have one term that has 5 and another term that has 3 and another term that has 7, then all of them have at least 3 of that variable, right? So we take that many out. We take out as many as we can from each one. But in this case, both of them share at most just a single a. So we're going to divide out 3a from both of these terms in the numerator. And it is important to realize we're dividing, not subtracting. So when we take 3 out of 12, then we end up with 4. And when we take a out of a to the third, we have 2 a's left over. That one does kind of feel like subtracting, even though it's not. When we take 3a out of negative 3a, then we get negative 1. This is the part where it's really important to realize we're not subtracting, because it feels like when we say we take this out of that, well, everything's gone, nothing's left. But when you divide it, when you divide something by itself, you get 1. And since it was subtracting initially, it still is here. So we've broken this down into 3a and then 4a squared minus 1. So that's a good start. We factored it out. But even after factoring it out, on some equations, we have to ask ourselves, can we box method it, or can we difference of squares what is left over? Well, this only has two terms, so we know we're not going to box method it. That's not really an option for us. But what we can do is we'll do a difference of squares, because if we look at each of these terms, we know they're subtracting, so difference, good. And every single thing here, 4, a squared and 1 is a perfect square, meaning that if we took the square root of it, we would get a whole number or a whole variable in a squared's case. So we're actually going to difference of squares this. Since I know difference of squares is the one that we do least often, and probably we want the most reminder on, I'm going to go through it. So difference of squares says we take our binomial and we break it down into two separate binomials. One of them adding, one of them subtracting. These are actually going to end up being known as conjugates. That's just the mathematical term for it. And what we do is we take the square root of every term in our original binomial. So the square root of 4 is 2. The square root of a squared is a. And the square root of 1 is 1. So we have 2a plus 1. The second binomial is going to be a mirror image of this, except with a minus instead of that plus. So we end up with 2a minus 1 here. So this is how breaking down difference of squares works. We have a plus binomial, a minus binomial, and then we fill in all the numbers that were originally there, but as their square roots instead of what they currently are. And that 3a is still going to be hanging out on the outside here. So this is the numerator, completely broken down and simplified. So that's going to be staying up top for us. We now want to look at this denominator and figure out how does it break down. So we ask ourselves, do we have anything in common to factor it out? Luckily we do. 12 and 6 are both divisible by 6. And one of them has a to the third, the other has a squared, meaning at minimum, like we were saying before, both have 2a's. So we have 6a squared there. What we will do is divide 6a squared out of both terms. When you divide 6 out of 12, we get 2 left over. When you take a squared out of a to the third, we have a single a remaining. And then just like before, we're dividing out 6a squared by 6a squared, like we're dividing out the same term. So what we get left over is a 1, but this time it's positive because it was adding initially. It was a positive 6a initially. This takes us to the second part of the problem. That is eliminating what I like to call our redundancies, or the terms that we have identically in the numerator and denominator. And we also get to simplify any fractions and that kind of stuff we have. So first we're going to talk about eliminating. When we look to eliminate variables and terms, I want to clarify that we cannot, and again, cannot take a look and say, well, there's a 2a and there's a 2a, let's just clear out those 2a's. We can't do that. Because for us to eliminate something, for us to remove it from the equation, what must happen if it is adding or subtracting something is everything must be identical. So we see a couple instances of adding and subtracting here. The 2a plus 1 is adding, these are subtracting, these are adding. That means these are entire units. That's why I like to write them with the parentheses around them as binomials, to denote that they are a singular term. So this cannot cancel out independently of that. We have to see the entire thing identically in the top and the bottom, if it is adding. If you have a number that is not adding anything, like that 3, it can cancel out with something else that is also not adding to anything. So if we just saw a 3 in the denominator that is not adding or subtracting anything, they could cancel out because there's no addition or subtraction. If there is addition or subtraction, then everything has to be identical. Now, luckily, we do see that here. We have a 2a plus 1 and a 2a plus 1. These can cancel out. They can go away, just completely be wiped out of the problem, leaving us with 3a times 2a plus 1 over 6a squared. This, again, puts us in the situation of saying, well, can we cancel anything more out? But as of now, we do not have anything identical in the numerator and denominator. Nothing looks exactly the same. So what we do at this point, now that we canceled out everything identical, meaning those addition or subtraction equations, then we will be able to simplify the fractions, or simplify things that we see have something in common in both the numerator and denominator. Now what I mean by this is, like, we see a 3 and a 6 here. If we were writing 3 over 6 as a fraction, just, casually writing fractions like you do, then we would simplify it or turn it into 1 over 2. We can do that exact same thing here. This 3 and this 6 can actually simplify to become a 1, which we don't really need to write because we don't really write 1s in mathematics whenever they're multiplying. And the 6 would become a 2. So we actually break it down to look like this now. And you go that one step further. But yet we still have one last thing that can happen. We have this a up in the numerator here, and we have an a squared in the denominator down there. If we think about what would happen to those, what would happen if we had a over a squared? Well, we know that whenever we divide variables like this, we're actually subtracting their exponents, and the difference, or the remainder, goes where the larger exponent was. So we would say 2 minus 1. Well, we have 1 left over, so that would keep that 1a in the denominator, because that's where more of them started, and we would have 1 over a. So we can do that again. This a and the a squared simplify to 1 over a. That just turns into 1. Again, we don't really got to write that. So we just have 2a plus 1 left in the numerator. And then that turns into just an a, so we have 2a in the denominator. Sorry, I went a little off screen there. I'm still getting used to all this. So this is our fully simplified version of the equation. This highlights what I was saying a moment ago, talking about we have a 2a up top and a 2a on the bottom. Can we cancel those out? No, we cannot, because we see the 1 in the numerator is adding. It has a 1 with it. This addition means that everything has to be the same. For it to cancel out, the 1 in the denominator will also have to have a plus 1. And since it doesn't, we cannot simplify those two instances of 2a. And this actually is just our final answer. So if you look here, we started with this big long equation, lots of variables, lots of numbers, all sorts of different things happening. And by factoring it to eliminate the redundancies and simplify the fractions like we saw here, we get it down to just be 2a plus 1 over 2a. There's still a couple variables, there's still a couple numbers, but it is not nearly as complex as it was originally. All right, so because of arbitrary time length restrictions imposed by the app I'm using, we have to cut the video there to not exceed the 15-minute mark. But I am going to do the second example on that page, number 7. You'll see that in a subsequent video that'll be posted here in a few. I'll try to link both on the Google Classroom, but if for some reason linking both doesn't work, if you just check out my YouTube channel, there will be a part 2 to this where we'll go over number 7.